Hello everyone. In this part 5, we'll be learning about a diffraction grating. So the outcome for this lesson will be basically you need to know at the end of this lesson that the interference pattern produced by light passing through a transmission diffraction grating demonstrates the wave behavior of light. The second outcome will be derive d sine theta equals to m lambda for intensity maximum in the pattern produced by a transmission diffraction grating, where d is the distance between the slits and theta is the angular position of the M or the maximum. And finally, describe how diffraction grating by very thin slits in a grating allows light from the slit to overlap and hence interfere to produce significant intensity maxima at large angles. So basically, what is a diffraction grating? Okay, diffraction grating is basically like what you see here, right? If you have a fence that's made up of vertical wooden blocks, right? So the wooden blocks are arranged in such a manner that the spacing between the wooden blocks, right, are basically even. So this forms a diffraction grating. In this case, there will be like something like 8 wooden blocks per meter. Another example would be like your comb. So you see the vertical lines. So this here forms a diffraction grating. Basically, in this case, it will be 10 lines per centimeter. However, if you want to see the diffraction of light, electromagnetic wave, we need a diffraction grating that's much smaller as compared to what you see here. So in the lab, you have diffraction grating like 300 lines per millimeter. So can you imagine in 1 millimeter length, can you draw 300 vertical lines? Right. So when light passes through a diffraction grating like what you see here, it's going to diffract. Okay, when we learn about Young's superslit, we learn about 2 light sources, S1 and S2. And we also perform geometrical construction to find the path difference between S1 and S2. So between S1 and S2, we can see S2 has to travel longer in comparison to S1. So how much longer is this much longer? So this is known as a path difference. In the case for a diffraction grating, instead of just considering 2 light sources, there are multiple light sources. Like the diffraction grating that I showed you just now, there can be 300 light sources, right? That's placed in 1 millimeter, right? So if we consider 2 adjacent light sources, S1 and S2, we can see that S2 has to travel longer in comparison to S1. So how much longer is this much longer? So this is known as your path difference. Just like Young's superslit, we can use trigonometry, that is sine theta, which is S2P, this distance, the one opposite, divided by your hypotenuse, right? So hypotenuse is actually the distance between S1 and S2, which we call it as D. So S2P is known as my path difference. And my path difference from trigonometry, I can find that it is equals to D sine theta. So D is the separation between the 2 slits, and theta is the angle that you measure from the perpendicular bisector to the point, interference point that you see on the screen. Okay, if you consider S2 and S3, we can see S3 has to travel longer in comparison to S2. So how much longer? S3P distance longer. So S3P represents the path difference between S3 and S2. And S2P represents the path difference between S2 and S1. So in other words, the path difference between S3 and S2 is still given as D sine theta. So this is true, right, for all sources, right? There can be 300 of them, and the path difference between each and every adjacent source will still be D sine theta, like what you see here. Between S8 and S7, we can see S8 has to travel longer in comparison to S7. How much longer? This much longer. So this is known as d sine theta. Okay, so how an interference pattern is produced on the screen, right, is basically when light passes through a diffraction grating, they are going to diffract and they are going to overlap with one another. So at a certain point on the screen, you'll see a bright light. So the bright light represents constructive interference. So to describe constructive interference is similar like how we describe the constructive interference for Young's double slit, that is d sine theta equals to m lambda. So in this case, d sine theta represents the path difference, and the path difference is basically this small triangle here, right? So rearranging sine theta, which is m lambda over d. So the question is, the angular position, right, theta, in the case for Young's double slit is very large. So why is it very large? The reason is because d is very small. Like the example that I gave you just now, the diffraction grating is 300 lines per millimeter. So imagine there are 300 vertical lines, right, in 1 millimeter length. So the spacing between two adjacent lines are very, very small. So from here, if d is very small, sine theta is large. So therefore, angle theta will be large. Okay, if we consider the interference pattern that we see below the central maximum, right, at this point, now we can see that between S1 and S2, S1 has to travel longer in comparison to S2. And let's say S4 and S5, we can see that S4 has to travel longer. It's much longer in comparison to S5. So it depends on where the interference pattern appears on the screen. It can be above here, or it can be below here. For the central maximum, why is there? How do you calculate the path difference for the central maximum? We look at this beam and this beam, the one right opposite the perpendicular bisector. These two beams have the same path difference. Right? So when these two beams meet up at the screen, you get constructive interference. Subsequently, the next one adjacent to it, and the next one adjacent to the most bottom, you find that both of these two beams, right, has zero path difference. So they will interfere constructively on the perpendicular bisector. Okay, so reflecting on our outcome, the interference pattern produced by light passing through a transmission diffraction grating demonstrates the wave behavior of light. So this can be seen from the diffraction of the waves and the interference pattern that we see on the screen. So derive d sine theta equals to m lambda. So how do we derive it? Is basically finding the path difference between two adjacent sources in a diffraction grating. It's similar like how we found the path difference for Young's double slit. Okay, the third one is describe how diffraction by very thin slits in the grating allows light from the slit to overlap and hence interfere to produce significant intensity maxima. So the reason why we have very large angles is because d is very, very small. Okay, next, sketch a graph of the intensity distribution of the maximum produced by a grating or monochromatic light. Okay, let's do this thought experiment. Let's take, for instance, if you have a light meter and you're trying to measure the intensity of light inside your room with all the windows open, right? And you do the experiment from 6 a.m. to 7 p.m. What do you expect your results to be? I would expect on a normal day, the intensity should look like this, right? At 6 a.m. it's still dark, so the room will be dark. Then the intensity of light gradually increases, right? Until it reaches maximum at 12 noon. And then intensity inside the room decreases until 7 p.m. becomes dark again. So this is known as your intensity distribution. So we can see the maximum intensity will be at a certain time, most likely at 12 p.m. So in this case, for Young's double slit, right, there are two ways to represent the interference pattern that we see. Okay, one is in terms of intensity distribution. That is, we can see, all right, this here is where the intensity is zero. Then this point is where intensity is maximum. Or you can also represent the interference pattern in the form of a photographic film. where you see constructive or bright light, then you see no light at all, and then you see bright light again. Okay, if you recall Young's double slit, the pattern that we see here is basically what I've shown you here is basically what we see from a photographic film. You have constructive, right, the bright light, then becomes destructive, no light, then becomes constructive again. So this maximum intensity refers to right in the center of the photographic film where the intensity is maximum. And this here is your perpendicular bisector. So if you recall why is there constructive indifference on the perpendicular bisector, it's because the light that comes out from S1 travels along this path to reach this point on the screen, whereas the light source that comes out from S2 travels along this line to reach this point on the screen. So you can see that the path difference is actually 0. So if I draw, right, let's say for instance, S1, when it comes out from this point, right, is a crest. So it's going to take 1, 2, 3 lambda to reach point P. There is point P on the screen. Whereas the light source that comes out from S2 is in phase with the light source that comes out with S1. So this is the crest and this is the crest. And it also takes 1, 2, 3 lambda to reach point P on the screen. So what we see will be a crest from S1 meeting a crest from S2. So a crest meets a crest gives you constructive indifference. Right? Okay, this point is the first order constructive, and this is again the first order constructive. So in the photographic film, you can see a bright spot right in the center. So first order constructive is basically somewhere around here. This is my first order constructive. So why do I get first order constructive at this point? It's because now we can see that S2, right, has to travel slightly longer in comparison to S1. Can you see that? This much longer. So how much longer? Since this is my first order constructive indifference, that means I know the path difference must be 1 lambda longer. So I can draw S2, which is in phase, right, with S1, but they are 1 lambda longer. Can you see this is 1 lambda longer as compared to S1? So S2 is going to take 1, 2, 3, 4 lambda to reach point P, but S1 is going to take 1, 2, 3 lambda to reach point P. But what happens is at point P is a crest from S1 meeting a crest from S2. So when the crest meets the crest, you get constructive indifference. Okay, at this point, from the intensity distribution, we see that this point is where the intensity is at its minimum. So from a photographic film, we don't see any light. So it's a black spot. So this is your destructive indifference. So from here, right, we can see that this point is destructive indifference. So the question is, why do you get destructive indifference at this point? It's because light source 2, all right, has to travel slightly longer as compared to light source 1. So how much longer we must take in comparison to S1? So since this is destructive indifference and this is my first order destructive indifference, that means S2 has to travel 0.5 lambda longer as compared to S1. So if I draw it, this is what I see. S2 has traveled 0.5 lambda longer as compared to S1 to reach this point on the screen, point P. So you see, right, when S1 meets point, when S1, right, touches the screen, it is basically a crest. And when S2 reaches the screen, it is a throw. So when a crest meets a throw, what you get will be destructive indifference. Okay, let's consider a point here. Can you see this point, all right? This point is basically, the intensity of this point is neither maximum, neither is it minimum. It lies between maximum and minimum. So it's somewhere around here. It's not maximum, neither is it minimum. So it's somewhere around here. So in this case, the path difference between S1 and S2 would be, let's take for instance, right, 0.6 lambda. So you see this S2 is 0.6 lambda ahead as compared to S1. So what happens when the two waves meet on the screen? You don't get constructive indifference, neither do you get destructive indifference. Okay, let me put numerical value. Let's say, for instance, right, when it's a crest, it's maximum, and it's 5 Newton per Coulomb, the electric field. Whereas S2, when it reach point on the screen, right, point P on the screen, it is -3 Newton per Coulomb. So when you use the principle of superposition to add up the electric field from S1 to the electric field of S2, I find that the electric field will have a magnitude of 2, right? 5 minus 3 gives you 2. So this is similar, like maximum is constructive indifference, minimum is disruptive indifference. So basically the intensity that is between maximum and minimum. So let's take for instance, if 12 p.m. is the maximum intensity. So let's take for instance at 2 p.m. You find that intensity in your room is neither maximum nor minimum. So there are cases, right, for Young subsystem where the intensity is neither maximum or nor minimum in this region, right? And this region as well. However, in our syllabus, we'll be describing constructive and disruptive. We'll not be describing any other conditions that lies between maximum and minimum. Okay, for Young subsystem, right, we can represent the pattern that you see in the form of a photographic film, or we can represent it in terms of intensity distribution like this. So maximum intensity, which is your central, then intensity gradually decrease until it becomes minimum, and intensity gradually increase until it becomes maximum again. Or it can be in terms of a photographic film, like what you see here, photographic. All right, so do not worry too much about the intensity here, which is maximum. All right, intensity first order maximum, they show that it's of the same intensity, whereas here they show that intensity has slightly decreased. So do not worry too much about what you see here. Okay, so for Young subsystem, okay, there are only 2 light sources. And for Young subsystem, the angle theta is very, very small. Okay, the reason why theta is very small is because the separation between the 2 slits are very large. Typically, right, the separation between the slits will be within 1 to 0.5 millimeter. So since D is large, sine theta will be small. So if sine theta is small, theta will be small. So when you see the pattern that appears on the screen, you see that first 0 order central maximum and first order, second order appears very close to one another. On the other hand, for a diffraction grating, we can have diffraction grating that has 100 lines per millimeter. Okay, how do you find D? So if there's 100 lines per millimeter, that means what we do is take 1 over 100 per millimeter, that means times 10 negative 3. And we have diffraction grating of 1,200 lines per cm. So what's the D in this case? Would be 1 over 1,200 per centimeter, that means times 10 negative 2 meters. So you see, right, if you compare the diffraction grating, the separation between the slits with that of Young's subslit, we can see that D for diffraction grating is very, very small. So if D is very small, that means sine theta will be large. And if sine theta is large, the angular position will be large as well. So if we see a diffraction grating, this will be the central maximum. And this here, you don't see anything, it's disruptive indifference. And then you see first order constructive. Unlike for diffraction grating, this is where you see central maximum, and this is where you see first order maximum, this is second order maximum, and so on. So they are very close together, but diffraction grating, they are very wide. Okay, so basically for Young subslit and diffraction grating, to describe constructive indifference, we still use the same formula, d sine theta equals to m lambda. For diffraction grating is also d sine theta equals to m lambda. So m will be your order of constructive indifference. For destructive indifference, for Young subslit, we use this formula, d sine theta equals to m plus half lambda. For diffraction grating, we don't use any specific formula. Basically, if m is not an integer, that's when you get destructive indifference. Right? When m is an integer, then you get constructive indifference. Okay, fringe separation. For Young subslit, we use this from the delta y is lambda L over D. But for diffraction grating, we use delta y, which is L tangent theta. Okay, the reason is because, right, theta here is very large for diffraction grating. For Young's subset, theta is very small. So if you recall in part 4, right, we derived this formula where we derive tangent theta equals to lambda L over D. We make use of the assumption that tangent theta is equals to sine theta. So that's why we can equate this. Okay, intensity distribution, like what I showed you in the previous slide, the patterns are very close together. However, for a diffraction grating, the patterns are very far apart. Okay, next, solve problems using d sine theta equals m lambda and describe how a grating can be used to experimentally determine the wavelength of light of a monochromatic light source. So when you solve questions related to this formula, we can see how unknown light source lambda can be determined by using a diffraction grating. Okay, example 7. So pause this video and try this question yourself for 4 minutes before resuming this video. Okay, so let's discuss. The intensity pattern from a diffraction grating and a double slit are compared. So using diffraction grating, yellow light of the first order is seen at 30 degrees to the normal of the grating. The same light produces interference fringes on the screen using a double slit. The slit separation is 500 times greater than the line spacing of the grating, and both the diffraction grating and the double slit are placed 1 meter from the screen. So in A, right, what's the fringe separation for a diffraction grating? And what's the fringe separation for Young's double slit? Okay, for diffraction grating, how do you find the fringe separation? We use tangent theta, which is delta y over L. Okay, so theta is given 30 degrees, L is given 1 meter. So you can find delta y. So delta y will be the fringe separation that is between adjacent maximum, between the central maximum and first order maximum. That is delta y. So using trigonometry, tangent theta is delta y divided by L. So we know L, we know theta, we can find delta y. So delta y will be 0.58 meters. Okay, now let's find the fringe separation for Young's double slit. So Young's double slit, we use this formula delta y is lambda L over D. So D here is very much larger as compared to the D for Young's diffraction grating. So it's 500 times greater than the D for diffraction grating. Okay, so what we need to do will be find lambda. So you can use the diffraction grating formula. So d sine theta is equal to m lambda. So since I'm describing the first order constructive indifference, that means m will be equal to 1. So I can find d sine theta equals to lambda. So d sine theta represents my path difference, and the path difference is just 1 lambda. So now, right, I can substitute this lambda into this formula to find the fringe separation. So lambda is d sine theta times L divided by D. So D here are common factors which I can cancel out. L is given as 1 meter, and the slit separation of a Young's double slit is 500 times that of a diffraction grating. So using all this information, I can find that my fringe separation in this case will be 1 millimeter. So if you notice, right, the fringe separation for Young's double slit is very much smaller as compared to the fringe separation for a diffraction grating using the same light. Okay, example number 8. So pause this video, and once you're ready, resume. Okay, in this question, monochromatic light of wavelength 590 nanometer is incident normally on a diffraction grating. So the angle between the two second-order diffracted beams is 43 degrees. So in this question, what's the spacing of the lines on the grating? So what this means is basically, right, when light passes through a diffraction grating, the angle between the first order to the subsequent first order is 43 degrees. So in other words, the angular position for the first order would be half 43 divided by 2, which is 21.5. So in this case, right, using this formula, d sine theta, which is m lambda, where we are describing the second order constructive, so m equals to 2, and we know theta, 21.5, we can find d. So d will be basically 3.22 times 10 negative 6 meters. Okay, often you'll find, right, questions where they say the light wave is incident normally on a diffraction grating. So what this implies is basically when the light beam comes in, right, here, the light beam comes in and struck the diffraction grating at 90 degrees. So when this happens, that means this angular position for the first order will basically be half that of this angle that you measure between the first order to the subsequent first order. If it strikes at an angle, then the interference pattern will no longer be the same. I mean, the angle here will be larger, the angle here will be smaller. It's very important to make sure when you set up the experiment, make sure that the laser beam strikes the diffraction grating at 90 degrees. Okay, example number 9. So pause this video. Try out these questions first. Okay, so let's discuss a diffraction grating experiment is set up using yellow light of 600 nanometer, and the grating has a slit separation of 2 micrometer. So the question is, what's the angular separation? Theta 2 minus theta 1. That means the theta 2 is the angle in which the second order constructive is seen, minus theta 1, the angle in which the first order constructive interference is seen. Right? So what's theta 2 minus theta 1 between the first order and second order maximum of yellow light? So in this case, what we do is let's calculate theta 1 using the first order. So d sine theta 1 equals to m lambda. So since it's a first order, m equals to 1. So we have d, we have lambda, just substitute the values, we can find theta 1. So theta 1 is 17.45 degrees. And we do the same for the second order. So second order will be d sine theta 2 equals to second order m equals to 2 lambda. So we find what is theta 2. Substituting the values, and we get theta 2 will be 36.86 degrees. So what's theta 2 minus theta 1? The answer will be 19.41 degrees. So take note, in a diffraction grating, theta 2 is not the same as 2 times theta 1. All right? For young subscript, then it is theta 2 is 2 times theta 1. Because if you see, right, in young subscript, the patterns are very close together. So when I want to measure theta 1, since delta y is very small, you find that theta 1 is the same as 2 times theta 1 is the same as theta 2. So the fringe separation between first order and second order is the same as the fringe separation between central and first order. On the other hand, for diffraction grating, the fringe separation between central and first order is not the same as the fringe separation between first order and second order. It becomes wider, wider, and wider. So between second order and third order, the fringe separation becomes even larger. So in this case, you find that theta 1 and theta 2 is not the same. So theta 2 is much larger than 2 times theta 1.